Hi all, and welcome to the Medical AI Lab Reading Group session. Every Thursday, a lab member covers a recent paper in either core AI or medical AI. This week, we will have Kathy Yu presenting the paper Geometric Deep Learning on Molecular Representations. So without further ado, I'd like to welcome Kathy to share this paper with us.
Thanks, Pranav. Hi, everyone. Welcome. My name is Kathy, and I'm a master's student in computer science at Stanford. Today, I'm very excited to be presenting the paper, Geometric Deep Learning on Molecular Representations. This is a review article that was published in Nature Machine Intelligence in mid-December 2021. So first off, let's look at what is geometric deep learning exactly. So as the name suggests, geometric deep learning is deep learning that incorporates geometric information. Specifically, it generalizes neural networks to Euclidean and non-Euclidean domains, including graphs, meshes, string representations, I will see later on. It incorporates a geometric prior. And a geometric prior is basically information about the structure and symmetry of molecular systems, and geometric deep learning tries to make use of these priors to improve the quality of its models and features. So now that we know what it is, we can then ask the question, so why do we want to use geometric deep learning in the field of chemistry for molecular representations? So there are two main benefits with using geometric deep learning as opposed to classical machine learning methods. The first benefit is that it is able to process unstructured data representations. As we know, neural networks can process images, videos, text sequences, and so on. And this flexibility is great for studying molecular structures and properties. The second main benefit is that deep learning is able to learn features automatically, so we don't have to rely on hand-engineered features for these systems. On the contrary, in classical machine learning, people often use hand-engineered molecular features called molecular descriptors. And with geometric deep learning, we don't have to do that. We can basically let the model figure out what are the best features to extract. And before we jump into applications and methods, we can take a closer look at key principles of geometric deep learning. In particular, we just learned that geometric deep learning incorporates geometric information. So what exactly is the important information to incorporate, and how do neural networks accomplish that? A key concept to note here is symmetry. Symmetry encapsulates the properties of molecular systems with respect to different transformations. So for instance, rotations, translations, and reflections. And there are two special properties. The first is equivariance. We can look at the notation first. So we have an input that's denoted by X, and we also have a neural network that's represented by F. We have some kind of transformation T and another transformation T prime for the feature space. So we can say that our neural network F is equivariant with respect to T via T prime if this equation holds. So what does this equation mean? This equation means that if we apply transformation T on top of X, take the output of that transformation and then plug that into F, we're gonna get the same result as when we directly apply F onto X and then apply some transformation T prime from the same symmetry group, but in some feature space. If this holds, we say that our neural network F is equivariant with respect to the transformation. We also have invariance. So invariance is a special case of equivariance where the second transformation T prime is the identity transformation. So combining these two equations, we basically have for invariance, the output of f of t of x is going to be the same as the output of f of x, regardless of what t is. So these concepts are very useful in studying molecular systems. Let's say we have a molecule, and let's say that the properties of this molecule does not change when we rotate the molecule, which is often the case. So basically, in this scenario, we can design a neural network that equivariantly transforms the molecule at each layer. And say, for instance, let's say we have a chiral molecule instead. Chiral molecules are molecules whose properties depend on the absolute configuration of stereogenic centers. So an example of chiral molecules would be DNA, where the direction of different parts of the molecule matter. So basically, if we apply, for instance, reflection on chiral molecules, we're going to end up with some other molecule with different properties. In this case, with chiral molecules, we don't want our neural networks to be reflection equivariant because we want to be able to differentiate between different molecules that are reflections of each other. We want to have different generated features for these molecules. And with these common transformations, we also have two special groups. The first is the Euclidean group. The Euclidean group basically includes all rotations, translations, and reflections, and also their combinations. We also have the special Euclidean group, which includes only translations and rotations, but not reflections. In the domain of chemistry, we often have various ways to represent our data. Here are some example representations of molecular systems. So image A shows a 2D structure that's called the Kekulé structure. So from this, we can see atoms, we can see bonds, and we can see different types of bonds, and as well as many other information. Image B is a 2D graph. And as we know, a graph consists of vertices and edges. And here, the vertices represent atoms and the edges represent bonds between different atoms. And in the third image here, we can see something called the SMILES string. So SMILES stands for the Simplified Molecular Input Line Entry System. And here we observe that we have different alphanumerical symbols representing different things, such as atoms, bonds, bond types, branching, and a lot of other information. And here, image D shows a 3D graph where we not only have vertices and edges, but we also have the coordinates of atoms in some 3D space. And then lastly, we have image E. This is a molecular surface. It's represented as a mesh, and the different colors here represent different atom types. So just from these examples, we can see that the same molecule can be represented in many different ways, and therefore it can be used by different methods and for different tasks. So next, I'm going to go over 4 of the most common types of molecular representations and talk about the specific methods that are used to process those representations. So first, we have molecular graphs. Molecular graphs can be either 2D or 3D, as we just saw in the previous slide. And the most common method used for molecular graphs is graph neural networks, also known as GNNs. So for a 2D molecular graph here, we have edges, we have vertices, and we also have features associated with each edge and each vertex. The typical approach here is to run a message passing GNN on the graph. So what does that mean? So basically, for every node in the graph or every vertex in the graph, we take features from its neighbors as the messages. And sometimes we apply a certain message processing function on these messages. And then we aggregate the processed messages from the neighbors. And we do this neighborhood aggregation for multiple iterations. And what we end up with is a set of node features and edge features that not only incorporate information about the node and edge themselves, but also information about the neighboring nodes and the overall geometric structure. And from here, with these features, we can do a lot of downstream tasks. So first, we can use, for instance, the node features to predict properties of particular atoms. We can also use node features combined with edge features to to predict certain bond properties between atoms I and J. And then finally, we can also aggregate all of these features in the graph and predict a molecule level property for the whole graph. Similarly, for a 3D graph where we have the added coordinate information, we can also do local predictions, such as atomic property predictions. And we can also aggregate information from all of the vertices and run molecular property prediction. And to be a little more specific here, commonly we see the special Euclidean group GNNs and also the Euclidean group equivariant GNNs. And if we use a SE3 equivariant GNN, we will be able to distinguish between stereoisomers of chiral molecules, including enantiomers. And also enantiomers basically mean molecules that are mirror images of each other. And then conversely with E3 equivariant GNNs, we can usually do computations in a more efficient way. Some common applications of molecular graphs include quantum chemistry tasks, such as predicting quantum chemical forces and energies for equilibrium. We also use molecular graphs for molecular property prediction for drug discovery. And here we note that GNNs, or molecular graphs, are particularly suitable for explainable AI because we can interpret molecular properties based on the specific nodes, edges that we have in the graphs. Molecular graphs are also used for de novo molecule generation, as well as computer-aided synthesis planning, also known as CASP. And here, CASP refers to the task of figuring out how to synthesize particular molecular compounds with certain desirable properties. And CASP typically would ask you to output the different reaction steps that would allow chemists to do that. The second main category is molecular grids. So we can consider a molecular grid to be a graph with some special adjacency configurations. It's basically a graph where the vertices have fixed ordering that's defined by the spatial dimensions of the grid. It's also a graph where vertices have identical numbers of adjacent edges. And from these properties, we know that we have a strong geometric prior for translational invariance. And just like graphs, grids can come in 2D or 3D. And generally speaking, the 2D grids are usually used for visualization purposes rather than prediction. And we usually use 3D graphs to capture the spatial distribution of molecules. In particular, we use CNNs for tasks on molecular grids. They're generally more resource efficient compared with equivariant GNNs. And because of that, CNNs are the method of choice when protein structures have to be considered, because protein structures are usually large and equivariant GNNs are usually applied onto smaller molecules with fewer than approximately 1,000 atoms. Next, we can have molecular surfaces. A molecular surface is the surface that encloses the 3D structure of a molecule at a certain distance from each atom. And points on this continuous surface can carry information about the molecule's chemical information, geometric information. And we can typically represent the surfaces as 3D meshes in space. One example application of molecular surfaces is using geodesic CNNs to predict protein-protein interactions. So geodesic CNNs are basically CNNs that are generalized to manifold surfaces. Molecular surfaces are a category of representation that's less frequently used and is currently at the forefront of research. Lastly, we want to look at molecular strings. So a molecular string is a linear sequence of alphanumerical symbols that represent the molecule. An example of this is the SMILES string that we saw at the beginning. And note here that SMILE strings are the most commonly used strings in this field. We can consider molecular strings and their corresponding systems as a chemical language. This language also comes with its own syntax and semantics. And the reason why this language has syntax is because these string systems also have rules with regards to what forms are valid and what forms are not. And the language also has semantics because a molecular string carries information about the underlying physiochemical and biological properties of a particular molecule. So we can treat molecular strings as sequences of tokens, and therefore we can apply common sequence modeling approaches on molecular strings. And the two most common approaches are RNNs, recurrent neural networks, and transformers. And applications using molecular strings include, for instance, using RNNs for molecule generation, where we are sequentially predicting the next token in the molecular string. Research has found that RNNs are great at learning the SMILE syntax and semantics. People have also used RNNs for molecular feature extraction. For instance, the Frechet ChemNet distance is a distance that's computed based on an RNN model, and it has become a very common way for computing molecular similarity. There are also many applications with transformers. For instance, people have used transformers for CASP, computer-aided synthesis planning, for molecular property prediction, property optimization, and new molecule generation, as well as for protein structure prediction. So here is a summarizing table that the paper presented. It includes the 4 types of molecular representations that we just went over, as well as the typical geometric deep learning approaches and applications associated with these representations. Since this paper is a review article, it provides a large number of cool examples and great references to different methods and applications. So if you're interested, you can definitely go to the paper and then look at the particular references. Lastly, I want to go over the future impact and research directions that the paper mentioned in geometric deep learning. So first, as a recap, we see that geometric deep learning acts as an alternative to classical machine learning and hand-engineered molecular descriptors. We also saw that there is a great diversity in ways to represent molecules. And subsequently, because of these different representations, we have developed different approaches, and we also saw that different representations work well for different types of tasks. Some of the patterns that we have noticed include molecular strings are great for generative deep learning tasks because we can take models that work well for natural language and other next token prediction or sequence to sequence tasks, and we can take these models and apply them directly on molecular strings, such as the SMILE strings. Secondly, we also observe that molecular graphs are a great medium for property prediction because molecular graphs are very interpretable, and also we can easily incorporate information we know about atoms and bonds, for instance, as node and edge features in the graphs. The paper also proposes many promising and interesting future research directions. For instance, the paper argues that we need to develop a proper understanding of the trade-off between algorithmic complexity, performance, and model interpretability. It's also important that we further explore the potential for molecular feature extraction. And along with that, the paper argues that we need to have a systematic way of evaluating how good and useful the extracted features are. In addition, drawing ideas from classical machine learning work in chemistry, the paper also argues that we want to have applicability domain assessment, which is basically a mechanism for identifying parts of a chemical space where a model can work reliably, can work well. The paper also advocates for trying out the less explored molecular representations other than the ones that are commonly used today. And one example of that is to explore the quantum and electronic featurization of molecules. And here are some resources on geometric deep learning. The first one is a link to the paper. If you're interested in the topic, you're very recommended to take a look. So this concludes my presentation. Thank you all so much for listening.
Thanks for the great presentation, Kathy.